prove the following identities. I'll start with the identity in part A. I'll show that the right hand side, when simplified, is equal to the left hand side. The right hand side itself is equal to sine theta over 1 plus cos theta plus 1 plus cos theta divided by sine theta. The first idea which would come to mind is to add the two fractions and hope that by simplification one would end up the left hand side. So we try this possibility. The common denominator is 1 plus cos theta times sine theta. Now 1 plus cos theta times sine theta, the common denominator, divided by 1 plus cos theta is sine theta, multiplied into sine theta, that gives us sine square of theta, plus, now the common denominator divided by sine theta is 1 plus cos theta, times 1 plus cos theta, it is 1 plus cos theta as a whole squared. Now we can of course open up the square and see what happens. The denominator is still 1 plus cos theta sine theta, and in the numerator we would have sine squared theta plus, I'm going to use the identity a plus b squared is a squared plus b squared plus 2ab. That would lead to 1 squared plus cos theta squared plus 2 times 1 times cos theta. Now we observe that we can rearrange the terms in the numerator to get sine squared theta plus cos squared theta, which we can consider together, and then we have a 1 and a 2 cos theta, and in the denominator we still have 1 plus cos theta times sine theta. Now instead of sine squared theta plus cos squared theta, I can write 1, and then I also have 1 plus 2 cos theta divided by 1 plus cos theta times sine theta. I can add the ones to get 2, and then I can factor the 2, and I will have 2 times 1 plus cos theta. In the denominator I still have 1 plus cos theta times sine theta. I can now cancel 1 plus cos theta from the numerator and the denominator, and I would get 2 over sine theta, which is equal to 2 cosecant of theta, which is the left hand side. Therefore we have proved the identity in part A. Now I want to show that part A can also be proved by another method. So I'm going to provide a second solution. This time I'm going to use half angles. The right hand side, I will write it again, it is equal to sine theta over 1 plus cos theta plus 1 plus cos theta over sine theta. Now I can use these equations. Instead of sine theta, I can write 2 sine theta over 2 cos theta over 2. And instead of 1 plus cos theta, I can write 2 cos squared of theta over 2. These are exactly the double angle formulas. However, I've used theta over 2 instead of theta in the double angle formulas. If we do the substitution, we would get, for the right hand side, instead of sine theta, 2 sine theta over 2 cos theta over 2 over, and instead of 1 plus cos theta, I would get 2 cos squared of theta over 2, that I can write as 2 cos theta over 2 cos theta over 2. For the second fraction, instead of 1 plus cos theta, I can write 2 cos squared of theta over 2, or 2 cos theta over 2 times cos theta over 2 divided by, and instead of sine theta, I can write 2 sine theta over 2 cos theta over 2. Now these fractions can be simplified. Cos theta over 2 and cos theta over 2 from the first fraction, 2 and 2 as well. And then we have a 2 in the numerator and the denominator of the second fraction, and then a cos theta by 2 from the numerator and the denominator of the second fraction. This is what we find. Sine theta over 2 over cos theta by 2 plus cos theta by 2 over sine theta by 2. Now here we might be tempted to write tangent of theta by 2 plus cotangent of theta by 2, but that would not bring us closer to the left hand side of the equation, which is 2 cosecant of theta. At this point I will add the two fractions, however, and I will find for the common denominator cos theta over 2 sine theta over 2, and for the numerator sine squared of theta by 2 plus cos squared of theta by 2, which happens to be 1. And in the denominator I can rearrange the terms to have sine theta by 2 cos theta by 2, which is quite familiar. I can now multiply the numerator and denominator by a 2, and I would find 2 over 2 sine theta by 2 cos theta by 2, with the numerator being the same as sine theta, and this is 2 cosecant of theta, which is the left hand side. As we observe, most of the times there is more than one way to do to prove an identity. Now let's look at part B. We are asked to prove that sine x minus cos x plus 1 over sine x plus cos x minus 1 is equal to sine x plus 1 over cos x. By a close look at this, what I call for now equation, because we're not sure if it's an identity, we observe that it is not quite obvious how we can reach from the left hand side to the right hand side, or from the right hand side to the left hand side. There is, of course, at least one way that I can imagine to do this, which is not quite easy. In this case, I'm going to use another technique. That would be working on both sides of this equation and show that we can reach an identity which is obvious and trivial or proven in the past. And then I would also need to show that I can do all the steps backwards to reach the equation for all values of x. And then I would have proven that the equation is actually an identity. So I am going to simplify the equation. In other words, I'm going to mix both sides using the rules of algebra. If I do a cross multiplication, I would get cos x times sine x minus cos x plus 1 is equal to 1 plus sine x plus cos x minus 1 times sine x plus 1. And I can simplify the left hand side. I would get cos x times sine x minus cos squared of x. So I am distributing cos x into the terms, plus cos x is equal to sine x times sine x, which is sine squared of x, sine x times 1, which is sine x, cos x times sine x, and then cos x times 1 times 1, and then minus 1 times sine x, and then minus 1 times 1, which is a minus 1. Now I see that I can simplify cos x times sine x from both sides of this equation. Also cos x and cos x. Sine x minus sine x would be 0. We are left with minus cos squared of x on the left hand side of this equation, and on the right hand side with sine squared of x minus 1. If we take the cos squared of x to the right of this equation and minus 1 to the left, we would have 1 is equal to sine squared of x plus cos squared of x, which is something we know to be correct. Now we need to show that we can repeat all of these procedures backwards. So we start, okay, now proof is presented here. We start with this identity, which is well known for all values of x. Then we take cos squared of x to the left side of this equation and 1 to the right. We would get minus cos squared of x is equal to sine squared of x minus 1. As you can see, I am repeating the steps backwards to make sure that I can reach the identity. Now I'm going to add cos x to both sides of this equation, and then cos x sine x to both sides of the equation, and on the right hand side I'm going to add a sine x and the minus sine x. I'm going to have cos x sine x minus cos squared of x plus cos x equal to sine squared of x plus sine x plus cos x sine x plus cos x minus sine x minus 1. And if we do the necessary factoring on both the left hand and the right hand side, we would get cos x times sine x minus cos x plus 1 is equal to sine x plus cos x minus 1 times sine x plus 1, which can also be written as sine x minus cos x plus 1 over sine x plus cos x minus 1 equal to sine x plus 1 over cos x, which is the identity we wanted to prove. Now, to show you that we really need to always demonstrate that we can repeat the steps backwards, I would like to mention an example. Let's imagine x is equal to 2. From this statement, we can conclude that x squared is equal to 4. But are we allowed to go backwards? I mean, if x squared is equal to 4, can we claim x is equal to 2? The answer is obviously no, since x may be minus 2. In other words, x squared equal to 4 implies that x is equal to, or x is equal to negative 2. This is an example, a very simple example, in which we can show that this process is not necessarily reversible. If from equation 1 we can get equation 2 by standard algebraic procedures, it does not necessarily imply that from equation 2 we can get equation 1 necessarily all the time. From equation 1 you can go to equation 2, but can you all go backwards? That is something that we have to verify for every single case.